All right, this is Embedded Systems, and today we're going to continue our discussion on scheduling. And remember, we've already been through this exercise, right? And you did have one that you did as a team, right? And we took a look at that. Now, one thing I should mention is that you never know when something like this will show up in a quiz. All right? So, and you never know when it might be helpful to do homework number 10 before you come to the next class.
Okay.
So when does homework number 10 due? Thursday. So, I think it's after next class, right? So you never know when that would be very helpful to do something like that. All right, so just to recap, since this class is being recorded 1 week after we did this, because we celebrated the holiday of eating turkey. For those of you who experienced eating turkey for the first time this week? Oh, none of you vegetarians kind of knuckled under, right? Oh, some of you just ate turkey all the time anyhow, right? All right, we'll go on. So, if we take a look at this example, again, we have well, let me step back and say there are a couple of variables and a couple of constants to keep in mind. One is this variable here. So each task is going to have a variable that says run. This variable will be the value of 0 or 1. I've just not put zeros here because otherwise you wouldn't be able to see the important aspects of this. And in fact, in this case, I make it bold if the variable run has been set during that time frame, or that time frame. Then you have another variable which is called time, which is a running counter as to how much time, how many timer ticks will occur until you count down from 1 to 0. And then there is a stored variable here called frequency, and that tells you what this value right here in time is going to be reset to every time that you count down from 1 to 0. Inherently, and we'll see this in the application programming interface, will be this variable here, or at least the priority will be identified in a structure, and you'll see that later. This is actually for our use to examine how long certain processes take to run. And one thing I should go into a little bit more specifics is actually what one of these time steps, what happens during one of these time steps. So to do that, I believe I'm going to need to take a look at this. And this is going to be looking at what happens in your machine. So as your machine runs a certain task, for example, let's say it's actively running T1. Suddenly, an interrupt will occur. This interrupt is associated with the frequency. Remember the frequency, or this is what I showed up here, the frequency associated with how often are we going to have, how much time does this take? So if we said that this time right here takes 2 milliseconds, let's say, or 1 millisecond for that matter. Let's do it really easy, 1 millisecond. Is going to be, how much time is in between here? At this point in time, an interrupt occurs. whatever T1 is doing is going to be suspended for a very, very little amount of time. And instead of T1 running, what it's going to run is the scheduler, very short amount of time. And then when the scheduler is done running, then it goes back to what it was running previously, in this case T1. As an example. Now during the scheduler time, and again it is very brief. Did I spell that right, brief? Or is it EI? I before E except after C. Okay, so that's right. So during that short little scheduler time, you're going to be doing the following. You will check each of the tasks. See if it needs to run. And how would you make sure that to see if it needs to run? So based on what we saw here, how would you know if it's time for it to run? This goes from 1 to 0. All right? Check each of the tasks, see if it needs to run by. So if the time of task variable so what does that mean right there? Minus before the time of task variable. What does that stand for in C? Guys? Predecrement, right? You know, if you have something like I minus minus, what does that mean? Predecrement, right? If the predecrement of the task variable is 0, so in other words, if you decrement the variable and it goes from 1 to 0, then the time of task variable is set to what? It's frequency, right? And also, you set the run of task variable to 1. Emphasis on you don't check the variable, you don't check the time or the run of task variable to see if it's 1 already. You just change it to 1 anyhow. Because as we saw in the example up here, in an extremely overextended system, you may actually set the variable to 1 when it is already 1. So as you notice here, every time when it goes from 1 to 0, then you reset it to the frequency. In this case here, the frequency is 10. And then you set the variable here to 1. And that is done in the scheduler. And that is done for every task. Now, notice what we're doing here. We're only setting flags, right? We're not actually running any task code. So back up here, for each of the subtasks. So it looks like it's going to be a loop of some sort, right? So the scheduler runs for a short amount of time. It identifies what has to run. When you exit out of an interrupt, what do you return to? What task do you return to? Or what program do you return to? Whatever was running previously, right? And And the way we talked about our round robin, it is completion. So you run to completion. So if T1 was running, you just keep on running T1. And so, lo and behold, you get to the end of this time, and maybe you'll be done. And then maybe you'll go down and you'll run the scheduler. So somewhere down here, it's going to be, for a very short amount of time, idle. In most cases, right? And then it'll go from idle up to the scheduler. And maybe in the process of the scheduler, it finds that there's nothing else to do, and then it goes back down and is the idle task. And then the idle task means what? Wait. Literally, all you do is you're sitting there waiting for some task to be scheduled. If you look at Microsoft Windows and you run the task manager, you can see, oh yeah, there's the system idle task or whatever it is. You know, you've seen that before, right? There's that wonderful process called that's taking all of that CPU. Have you ever wondered why it's taking so much system idle process? Why is that taking so much time? And the answer is? It's a computer. Something has to run, right? Now, in an embedded system, sometimes that might be a sleep process or something like that, right? Where the system actually goes to sleep and nothing runs. But in a computer where it's running all the time, there you go. It's taking up 99% of that time. Darn that system idle task. So back into here, this is an example of what we're going to do. Now we're going to look at how we're going to set up all of these tasks that we're going to run, how we're going to ensure that the scheduler is going to run. So I gave you what was called a application programming interface. And so this application programming interface said that we had the following tasks. One that was, do I actually have a name for these? Oh man, we're going to have to find a good example of that. In fact, I'm going to address it now. Here we go. So we have these application programming interfaces, and we have, well, we're going to start up the round robin scheduler. We're going to add a task. There should probably be, oh, I guess there is there's no space between these, so it's all squished together. Remove task, run robin scheduler. Oh no, I'm yawning. That means I'm boring myself. All right, so let's look at some of the important ones. Add task. To it, we identify what the task is going to be. So it is the address in memory of that function. And we'll show you how to do that in a few minutes. The time period, meaning how frequently this is going to run, and then what priority it's going to run. Remember we saw in the example, let's see if I have it on the next page. Nope. We saw in the example that you could run priority 0, 1, 2, 3, 0 being the highest priority, 3 being the lowest priority. You can enable tasks and disable tasks, and then of course run them. So let's take a look at what an example of this. So, oh, by the way, we might want to set up a timer. Ooh, I need to change this slide. We can set up a timer that will generate an interrupt every 1 millisecond, right? And, this is, just ignore what this is. This is a word processor. In fact, that might be a very good quiz question of how would you set up the timer to create an interrupt every 1 millisecond? So I'll have to add this in as a test or quiz question. how would you set up the timer for round robin? So, here's the important aspect of this. What is the structure of what we are doing? So, obviously, here is the initial timer value. That's the frequency, which I've discussed before. There is the current timer value, which is what you count down. Here's that single, I'll identify it as an int, but it's really just a simple binary. It's either 0 or 1. Binary 1 means run now. It means enabled. In other words, you can actually create a task and then not run it yet. And then you can turn it on and off. Here's the other thing that's interesting. Look at this. Void star tasks void. What this will do is this will identify an address for a function. So you're looking at the beginning address or the first address that you will load into the program counter for running that task. So we're going to be able to store the address that you're calling here in your structure. Then we're going to create a global task, and in this case we have only 5 tasks we're going to run. And the other things are identifies if we want to use round robin or not. So let's take it a lovely little example. Remember how I said here the scheduler is running, and I showed you in my little situation here. Here's the time spent running the scheduler. All right. So here is the scheduler. The scheduler is an interrupt service routine. And it will, hold on, no, I take this back. This is just running the general scheduler, it's not the interrupt yet. So while 1 forever, so I take this back, this is the general scheduler that is running, not the interrupt part of it. And for I equal to 0 to the max number of tasks, so you're going to check each one of the tasks in a structure. First you're going to say, is it a task that actually has some sort of address in it? In other words, have you said, yeah, I'm going to run a task, and here's the address for that function? So if it's not no, that means there's actually something that can run. You have to see if it's enabled. And if it is enabled, then you have to see if it's scheduled to run. So if the run bit is equal to 1, then you change the run bit to 0, and then you actually execute the task. Now notice once you go here to execute the task, and you're done, you break out of what? Which level? All the way out to the while? So this break, after the task is done running, and it ends, in other words, the function is done running, you come across a break. So according to the rules of how C runs, you're breaking out of what? So the last if, you're breaking out of the for, which will take you to the while. So what this tells you is that once, for example, task 1 completes running, or whatever the highest priority 1, let's see, what's the priority 1? First priority is task 2, then task 1, then task 3. So if it turns out that the highest priority task 2 is running, and it finishes, then it will go back and it will check if 2 should run again. So if 2 has high priority and it runs for a long time, and it runs very frequently, there's a potential for you not being able to run some of the ones later on. You all understand this, right? Now, here's how we initialize a task, or all the tasks. First of all, we're going to go through each one and just give it timer 0, run 0, 1, enabled 0, and null. Actually, I'm looking at this. This is a typo here. This should be, let's see what my, it should just be, oh, or is that correct? So in other words, enabled is equal to 0 and timer is equal to 0. Can I do this? Do I have to put the dot in front of it, or can I do it just like that? Yeah, I think I might need to put the dot in front of this, and this part of the global task is assumed. But you know what? When you're writing code, it would be just as well just to put the entire thing right after that. Just to write everything else. So I'll have to fix that. All right, so let's say we want to run a task. We have this function here called adding a task. And actually, running something, if we want to, for example, identify something to run, our function is called flash red LED. Its frequency will be 25, and its priority will be 3. So what has higher priority, sample ADC or flash LED?
Flash LED.
So flash LED has a higher priority because it has a lower number according to our algorithm. And look at this is only happening every 50 milliseconds, let's say. So when you identify that you're going to add a task, first thing you do is you check to see if the priority that you passed into this function exists. And if it's okay, in other words, if the priority is valid and it's null, then you can go ahead and schedule the task. In other words, here you go, you're scheduling the address of the function, you're setting it to not run, here's the default time that it's going to run, it's enabled, and then the initial timer value, in other words, you're starting at its full frequency and you're going to start counting down. Notice that you're putting it in your global task list in the specific priority. So if you set your priority as 1, then it will put it into the second structure for this list. Now notice here we have the interrupt. Specifically when a timer tick occurs, we're going to go through for each task, starting from 0 to however many tasks you have. If it's not null, in other words, if you have already provided some sort of address for that task, then making sure that it's enabled, then making sure that the timer is non-zero, then you pre-decrement that value, and if it's equal to 0, see that's a double equal, it's kind of squished together. If it's double equal, then you set this list to run, and then you just set it to the initial timer value. In other words, you go from this 10, or from this 1, counts down to 0, and then you identify, yeah, it's time to run. If it's equal to 0, you set that to 1, and then you reset this to the original frequency of how often it goes. Everybody clear on that? You never know when something like this will show up on a test or quiz. If you want to remove a task, simply you identify which task it is, and then you will just wipe it out. You can also enable and disable a task just by changing the specific task number. In other words, the priority of it. You could also do some changing of it. In other words, identify how much time it will take. Change the time on that. And then to start my scheduler, we're just going to run the round robin scheduler. See, is that it? So that was a specific example on round robin, and something I want to just go over in general is some other types of scheduling. So that was the run to completion scheduler, and again, the limitations of this was associated with you have to complete the task that's running, and if you have something that takes an awful lot of time and it starves other processes, you may start to lose data. And it is prioritization unfair. Remember how I noted that once it's done executing it, then it starts at the beginning of the priority again? So if it finishes executing, it checks not ones that have been there waiting longer, but have higher priority. Now, is that a bad thing? Usually, there's a reason why you have a priority for your tasks, right? So maybe priority is not bad, but if you have a very busy system, there may be situations where you don't execute some of your tasks. There is also a possibility for you to create a queue of tasks that need to run. So when you identify this queue of tasks that need to run, you can build up, very similar to what you did with the application for the queues for communication. You can enqueue and dequeue different tasks that you have running. That way you can try and be more fair. So whoever comes first gets the first ability to run. And of course, you still need to run to completion in this case. Again, you must wait for the completion of that specific task. So, if the lowest priority functions never get to run, maybe because you keep on enqueuing different tasks in higher priorities. And one other possibility that I've seen is as follows. In some examples, you have multiple queues. And what you can do is create a linked list. Have I done this before? This seems familiar. By the way, this ground means what? Last node in the linked list, right? So there are situations, or there are systems where you can actually set priorities of different tasks at the same priority. So maybe you have the flash LED red and flash LED blue as priority 2. And this could be the flash red, flash blue, flash green, and you don't really, those aren't high priority, but this could be the audio 1 task, and this could be the RS-232 one, receive, and this could be RS-232 transmit. These are tasks that are ready to run, and you're putting them in a queue. So let's say suddenly I have another task, which is a priority 1 task, and I want to add it to my queue of things that need to run. This priority 1 task will communicate via, I'll write to the LCD. So now I'm going to have the LCD task that needs to run. And that will be then the last one there. So I will add it to the priority 1 queue. And when I'm addressing all these tasks, I'll do this one first, this one second, this one third, this one fourth, this fifth, sixth, seventh, eighth. If suddenly I add another task, so for example, if I add a what's another nice peripheral? Accelerometer task. So I add my accelerometer task here. While I'm still running the audio one, then this becomes 1, 2, 3. This is now 4, 5, 6, 7, 8, 9. And if I have another task coming up, who knows? See, this was flash. Red, blue, green, whites. I'll have another one, flash, purple. I'm stretching right now, all right? Add it to the end of this, and this is the 10th. Even though I added it later, it's the lower priority. So this is an example of a scheme where you could have a queue of tasks at different priorities. Again, extremely low priority task right here. That if you continually add priority 0 and priority 1 tasks, you may never get to these at all, period. And that's one of the problems associated with, well, in this case, an overloaded system. But imagine this, if you don't have an overloaded system, that means that you should be able to reach all of these at one time, or within one time tick, or at least fairly frequently, right? So this just tells you the priority that you need to address it. Does a human need to see a flashing LED really frequently? They can't tell the difference between a 1 millisecond flash and a 10 millisecond flash. However, if you don't handle the audio quickly, you may lose that data. And so that's why you would do a priority scheme like that. This tells you again, the lowest priority function may never get to run if you have a really overloaded system. Now, I've talked about a real-time operating system with a kernel. So, notice that the ISRs handle most of the urgent operations. And then the other code just finished when it had time. With a real-time operating system, a true RTOS can suspend a task to run something that might be of a higher priority and preempt it. And that's the important thing, is that the more money you pay and the more code you put into the scheduler, you can do things like try and ensure fairness, allow everybody to have a chance to run, or interrupt something that's running and take care of your new task that's even more important than anything else. And again, this is just motherhood statements. You can read this as well as I can. That a real-time operating system actually is the piece of code, specifically inside of a kernel, typically, that can handle who gets what when you're doing this, or who gets the resources when you're scheduling. So what's the biggest resource in a computer system? The processor, right? So the scheduler not only handles who gets the processor, but the scheduler can also handle who gets other resources, like disk drives or RS-232 ports or displays. Let's see. There is a tool called MicroCOS, YMMV. You know what that stands for? Your mileage may vary. So in that, the number of compute cycles for the real-time operating system was 4% of what the CPU was doing. So the scheduler is taking 4% in this free RTOS system. Is that a lot of time? To ensure fairness? To share resources? Actually, it's not all that much time. And look at this, it's only 8.3 kilobytes and 5.7 kilobytes of data memory and code. So, in essence, this RTOS is a pretty good idea. We'll be looking at this in the advanced embedded systems course. We'll be looking at micro-COS. So again, when you're looking at priority levels, Robin, pretty much all the code has the same priority, but with interrupts, then certain ones can have higher priority based on where it sits in the ISR chain. And then also, if you have RTOSes and function queues, you can have further resolution of that. So, this will just give you a comparison of all the different ways of doing it. The important thing to take a look at is simplicity. Round robin is really simple. And in fact, the first exercise for the real-time, or for the advanced embedded class, will be to implement round robin. You can feel free to implement it for lab number 6, but it's not required. Then we'll get into more complex ones, where you're handling a lot of resources with the real-time operating system. Things like memory and who gets to run when. All right, so we looked at, I went over this, we did this, we did this. We'll see how far I want to get into this. All right, so if we look at one of our applications, we've looked at this before, right? An answering machine. And this is a really simple one. Hey, look what we have. We have some microcontroller, which is going to use some keys. We have all of this hardware out here that will allow us to do things like take our telephone line, A to B conversion. Excuse me. And record messages, right? So if we want to put an operating system on this, how would we handle this in a design with respect to operating systems, with respect to shared memory, with respect to making sure everybody got a chance to share the processor? So let's just take a look at the delete function. Now, let's look at the architecture again. Where are we storing all of our data? We're storing it on a message memory, some sort of SD-RAM or flash. And the way we work, we can actually use direct memory access and send some data down here and have the processor do other things. Or maybe we have to wait for we can send a message to the display and wait for it to come back to us and say, yeah, I displayed it, I'm ready to go. So let's take a look at an example. We'll want to put, if we're deleting a message, we'll want to put a message on the LCD saying, are you sure? Then we will wait a maximum of 5 seconds, but a minimum of 400 milliseconds to wait for the button that says yes. You know, this is simple. It doesn't take voice command, right? Most of them now use voice command. So this one will be, you have to push a button that says yes. So if you actually say yes, then you will erase a message. You'll delete it as you asked. If you press the no key, the cancel key, then you'll just put to the LCD something that says cancel. Notice here it takes 10 milliseconds to write anything to the LCD. Here's another one, timed out, 10 minutes to the LCD, else, etc. And there are little things, like if we're erasing, then we're going to need to send some data to the flash buffer. We're going to have to read and find some offsets, change the linked list. Remember, we looked at this problem before. We're saving stuff on the linked list. We'll have to overwrite different parts on it. It takes some time, 20 milliseconds. Now, if we ran this sequentially, we would display sit around, wait. When it came back, then we would do this, sit around, wait, come back to this, sit around, wait. Wouldn't it be nice to just send something off to the LCD saying erasing, and then at the same time, you could do this task, this one, this one, this one, this one, and you can pretty much do a lot of these tasks at the exact same time. These ones that have you touch the flash and the LCD can pretty much be done at the same time. So we can create some sort of functionality that, based on this, it's not so much sequential, but we can actually do some processing of all this stuff at the same time. So how do we split it? Well, let's take a look. Hey, does this look like something very similar you've seen, even though it's kind of flowing down? What kind of construct have you seen that's been similar to this before? Where you flow from one state to another state. All right, yeah, state diagram. So perhaps you could do something like this. You could set and make a state machine where you could say, are you sure? And you just wait for the state to switch. And based on, and then you're in this and you're waiting for the reply of the LCD done, and once the LCD is finished displaying, then you can start debouncing the switch, and when it's done debouncing the switch, then you can decide if it's going to be canceled or timeout or erase. And then if it's over here, let's see, current state 4, this is erasing, then you can start doing this work. Otherwise, you can just send some, look at this. You're sending it to the LCD, you're functioning, you're doing the function, right? Setting the current state to 4 when it's all done, returning up here. But this function right here could actually be a task that executes. They use slow devices, which make the processor wait, like the LCD. All you have to do is send information to it and wait for the verification that it's done. Wouldn't it be neat if you could just send something to it to say, yeah, do it, and when you're done, let me know. And that's why we have a preemptive scheduling kernel that you can work with that will force the processor to switch from one task to another. So in kernel mode, that's typically also something called supervisor mode. That's where the operating system works and you, the user, cannot work in that realm. So in other words, the operating system handles the resources for you. You have to ask the operating system for that resource. For example, in lab number 5 that you did, you literally controlled the UART, correct? Well, in the world of an operating system, the operating system would control the hardware port for the UART. You would ask to send, all right, you would most likely have a single function that says send the string to the UART. And then you would let the operating system handle all the timing and handle everything associated with sending that one string. And you would just wait for the response back saying, yeah, I did it. It all got sent, no errors. And that's what a kernel can do for you. Well, I'm not sure how far more I want to get into this. I think I'm going to do this anyhow. Wow, this is going pretty long, right? So I tell you what, let's take a short little 5-minute break, and then I'll start back up in 5 minutes. All right, so I've actually talked about this earlier, there are two aspects of operating systems. We could look at extended machine. In other words, it handles our file system, and for example, it'll make a disk and maybe 512 megabytes of RAM look like an even bigger RAM device. In other words, you don't have to worry about how you go out to the disk. You just have a single address, and it goes out and handles everything. And then there's other operating system features: sharing the processor, synchronization, memory management, file protection, file management, I/O device access. So we care mostly about preemptive thread management. In other words, how we're going to share the processor. So let's take a look at an example of sharing the processor. And let's say I have a processor with these following registers. Do they look familiar? Yes, no? All right. Now, in the old days, I believe you know what a stack is, right? You had that in your architecture. And so we have two flags that will point to the stack. One is the stack pointer. The stack pointer points to a location, to the first used or the first open memory location. I believe it's going to be the first used one. And then the frame base is actually used to identify where if you're in a function, this is where the previous function information exists. But let's just say it's just a register out there that you have to work with. In your memory, you'll have global data, you'll have a heap, you'll have instructions. And if we're running for one process, in other words, what you've done so far, you only have one stack, one set of global data, one set of instructions. And keep in mind that everything runs happily. You have your data registers up here, your address registers, your program counter. You're only executing one program, right? Now, imagine a more complex environment where you are running multiple things. In other words, a process, in this case, a process will define as no information is visible between processes. A thread shares the address space and code with other threads. And then all of these different types of pieces of software are running at one time. Keep in mind that each process that's running, or each thread that is running, has code associated with it that may be completely different areas of the program space. Remember our program space up here? So you could have one thread or one process that's running from code up here and another one that's running from code down there. And you're going to have to keep track of where it's running. Because remember, we're sharing our entire processor between multiple processes running at one time. So in other words, if we have two threads, thread A and thread B, they are located in this location and this location. They will have two separate stacks. Typically, global memory is shared amongst everyone because typically global data is where you can actually share information between multiple threads. And in fact, usually that's the way that you do communicate between multiple threads, is by using shared memory, some area of the mailbox. So if we have multiple threads, we should have some sort of control block. In other words, some way of storing where our information is going to be for these registers. Because for each one of these threads that needs to run, it's going to need its own program counter, right? It's going to need its own frame base and stack pointer because they exist in different stacks. It'll have its own flags as it's running. The only thing that might be the same is the beginning of the global data, which is our static base register. So what we'll do is we'll define this thread control block as someplace in memory that will actually store all of this information. So let's say we're running task A. Task A, remember, has this stack. It has all of this data inside of the CPU. And let's say we want to run another task. What we're going to have to do is somewhere in memory in this global data, or maybe in the stack, we're going to store all of this information from the CPU into this thread control block, this memory area. And so we'll just copy all of that data over here. Now at the same time, what we're trying to do is we're trying to switch to thread number B, or thread B. So to do that, we have this existing thread control block. In other words, all these registers that say what the state of this thread that was running. We're going to copy all of this data over to the CPU. So we'll need to get and identify where this memory location is, and then we're going to copy all this information over here to the CPU. So now if we start running this thread, the very last thing we'll do is we'll load the program counter with the actual next instruction to execute inside of thread B. Then suddenly we'll switch our context from A to B. So that sets up how we're going to use in our operating system all the different threads and all the different processes and the different states that they'll need to be in. And this is an important slide from the respect of how an operating system runs. I think I've showed this already, right? Didn't I draw a picture of this earlier? No? Anytime you create a new thread, it's new. And when it first starts, it will be ready to run. The operating system itself will switch our threads from one state to another. So in this case, if a thread is in the ready state and it's the highest priority, it will be switched to running. And perhaps the one that was running will be switched off to ready. It wasn't the highest priority one. So, like I showed earlier, thread A could have been running and we switched it to ready, and thread B was switched to running because it had a higher priority. Now at some time, a thread that is running will need some sort of resource. Maybe it's waiting for the hard drive or data from the hard drive. So the operating system will move it from the running state to the waiting for a resource state. And when a resource is available and that data is made available to the thread, then it becomes ready to run again. Now a thread may be running and then it's done. It's done everything it needs to, that it was meant to do. So it can be switched to the terminated state. So these are the main thread states that you need to worry about. And this is the states that an operating system will run in, or the thread will run in. And in fact, remember you have one processor. Now, I mean, you could have multi-cores, right? In this case, you would have one running process or one running thread for each core that you have. But you may have many that are waiting, and many that are ready, and many that are terminated, many that are new. And the operating system kernel will move it depending on the resources that are available and the priority of the thread. So again, our thread control state is going to have, remember how I showed earlier? This is the data associated with the thread that's running. Remember, the code is not changing. The stack, the data in the stack is only going to be changed by the thread itself. Thread A will only change this stack. And so if you want to switch between the different threads, the operating system only needs to move the thread control block into the processor to have it start running that particular thread. And what you'll often see is a priority of, oh, these are the new threads that need to run. These are the ones that are ready. These are the ones that are waiting. Remember, there's only one that is running. So in this case, you'll have, let's say, thread A, which is running. And it has its registers identified with how it is running. And then let's say you want to run the next waiting process. In this case, it will be the highest priority one, which is C. So what we'll say is, all right, we will take whatever our thread control or whatever this data is in our registers, and we'll copy it over to thread control block A. Remember, that's just memory. We will add, since A was preempted, we will add it to the end of our ready queue. This is just a linked list. Then we will take our thread C off of the ready queue, and then we'll copy all of the register data from memory into the actual central processing unit registers, and it will stop running that thread. And that is how you will switch between different processes running in our microcontroller. That is all I have for lecture number 26. Thank you very much. You are really sad and sorry.